Welcome back, Tamjid.
Yes, sir.
Here we have so background radiation, right? We are
Hmm.
discussing the background radiation. Background radiation. From this name, you understand that other than the radioactive source, we have some we have some sources in our surrounding area which are giving also radiation or count.
Hmm.
And when we did the experiment with nuclear physics during our student life in Dhaka University. That time we also found it that in Geiger-Müller tube, before giving the cesium or uranium sample, so in front of the Geiger-Müller counter, still we are having some, reading in the count meter. On the screen of count meter, sometimes it's coming 20, then sometimes it's coming 15, then 17. This way, even after we are not giving any radioactive source, this types of count is coming in the count meter. So why it is coming? It's coming from the surrounding radioactive sources. And these sources are two types. One is natural sources, another one is artificial sources. The natural one, we understand that these are radon gas from the ground, then buildings and the ground, cosmic rays, food and drink. These are the sources, natural sources. And the artificial one, we have medical, uh, in medical, we are also using some radioactive particles. Okay, we are using gamma rays. We are using, for cancer treatment, we are using X-rays. We are using X-rays for taking the, reading from the, you know, from a film, right? That that modes fracture, all these things. Yeah. And also, we have, you know, radioactive therapy for treating cancers. Yeah? Those
Like
sources. This
putting
is
gamma.
these are medical sources. Like one of the great writer of Bangladesh, Humayun Ahmed.
Yes, yes,
Heard him? You know his name.
yes, yes.
He got cancer and he was treated with radiotherapy. Yeah, and this way many people they are given radiotherapies. Uh, those are the sources of radioactive or radioactivity from medicals. Then other sources we have nuclear power and power stations and weapons testing. Those are also the sources for uh, you know these are man-made, right? All these are man-made. So when we are getting this background radiation, then we are recording it, yeah, in our physics copy, practical copy. We recorded it that this one is my background radiation. For example, it is 23 Then after giving the source, for example, we are getting the reading 1050. So in this 1050, that 23 is also included, right? Isn't it?
Yes, yes.
So when we are recording on the copy the emissions or the count from the source, that time we are subtracting this 23, 1050 minus 23, and then we are getting the value 1027. That one we are writing as the count from the source. Is it clear?
Yes,
So this way we are dealing with background radiation. Can you please read?
yes, sir. Radioactive materials occur naturally as as a result everyone is exposed to low levels of radiation every day. This exposure comes from a mixture of natural and man-made resources. Pie chart looking at sources of background radiation. These are from radon gas, building, cosmic gas, food and drink, and man-made. Man-made is broken down into another pie chart. The actual amount of radiation that a person is exposed to depends on where they live, what job they do, and many other things. Scientists must always take into consideration the amount of background radiation when working or experimenting with radioactive sources and discount it from their results.
Okay,
Yeah.
clear, right?
Yes.
This one is clear.
Sir, what type of question can come from this part?
This part, the one already I told you, uh, that one sometimes in our numericals, the background radiation count will be mentioned during calculating the half-life. So you will get some questions related to background radiation. Also, background radiation definition is coming, and sometimes it's coming. What is the main source of background radiation? So
Radon gas.
yeah, so this way it's coming, huh?
Hmm. Right.
And what are the man-made source? What are the natural sources of background radiation? This way also comes. Is
Hmm.
it clear?
Yes, yes, got it.
Okay. So if it is coming this way, you can solve, right?
Hmm.
Now, carbon dating. Carbon dating, before going to the discussion, I'm giving you some idea, little bit briefing idea. That
Hmm.
is, carbon dating is used for getting the age,
Date.
age
Oh, date. Oh,
uh,
date.
from for the ancient fossils like dinosaurs or the previous animals or plants. If the archaeologists they are getting them, their bones they are getting, there's any sample they are getting, then they are finding the age of them using the carbon dating process.
Hmm.
So how they are getting this carbon dating? Like if you are having one sample of any plants remains,
Hmm.
uh, and you are keeping it in front of any detector. We have now some upgraded modern detectors which can correctly get the emissions, right? Record the emissions. So
Hmm.
those detectors they can find or calculate from this reading how many years back this plant was available on this earth. How it's happening? I'm giving you a very simple example. Like for example, the sample of plant, if it is 5 kg, yeah, so it was supposed to have 5 gram of carbon 14 at the beginning. This is for example. I'm not saying exactly there is 5 gram in 5 kgs. It's just giving one idea how it's happening. Yeah. So 5 gram carbon 14, it was supposed to be at the beginning, right? Now you are getting only 1.25 grams. How much you are getting?
1.25.
1.25 grams. How you are getting this 1.25 grams? The scientists, the archaeologists, they have some standard that for 5 gram of carbon 14, how much should be the count in the detectors. So if, for example, 5 gram of carbon 14 should give 1000 count, but it's giving only now 250 counts, right?
Hmm.
Isn't it? So
Hmm.
if it is giving only 250 counts, that means it's already past two half lives,
Hmm.
isn't it? So two half lives means for carbon 14, one half life is around 6000 years.
Hmm.
Okay, then two half lives past means it was around 12,000 years back. This plant was on this earth. Is it clear now how
Yes,
carbon dating
yes.
is working? So this one we are having here in the discussions. Uh, Here we have discussions, and also in diagram it's written. You first read this description, then check out the diagram, then you'll understand. Okay, read.
This is how carbon dating works. Carbon is a naturally abundant element in the atmosphere, in the earth, in the oceans, and in every living creature. Carbon 12 is by far the most common isotope, while only about 1 in a trillion carbon atoms is carbon 14. Carbon 14 is produced in the upper atmosphere when nitrogen is altered through the effects of cosmic radiation bombardment. A proton is displaced and nucleophilically changing the nitrogen atom into a carbon isotope. The new isotope is called radiocarbon because it is radioactive, though it is not dangerous. It is naturally unstable, so it will spontaneously decay back into nitrogen 14 after a long period of time.
Yeah, continue please.
Uh,
Oh,
it takes about 5,000 5,730 years for half of a sample of radiocarbon to decay back into nitrogen. It takes another 5,730 for half of the remainder to decay, and then another 5,730 for half of what's left, then to decay, and so on. The period of a time that it takes for half of a sample to decay is called a half-life. Radiocarbon oxidizes and enters the biosphere through natural processes like breathing and eating. Plants and animals naturally incorporate both the abundant C12 isotope and the much rarer radiocarbon isotope into their tissues in about the same proportions as the two occur in the atmosphere during their lifetimes.
so you understood it, right?
Hmm.
How it's working, carbon dating.
Hmm.
Then here we gave also one example. The way I was saying that the plant's age is here 0. Then after half life, it's age 5730 years, one half life, two half lives, then three half lives. Okay, so its radioactivity is also decreasing. You see,
Hmm.
this way it's working. Now the final part, please read. Huh?
Hmm.
When a
First,
creature dies.
when a creature dies, it ceases to consume more radiation while the carbon 14 already in his body continues to decay back into nitrogen. So, what does this mean?
So it's saying that carbon 14 is converting to nitrogen, right? By beta
Hmm.
emission.
Hmm.
Uh, you already know that one, right? How it's converting to
Hmm. It,
nitrogen.
it loses beta particle.
Yeah, it's emitting beta particle by losing one neutron. The neutron is breaking down to proton and electron. So its atomic number changes and increases by one. It's turning to new
Hmm.
element. Is it clear? Mass number is same,
Hmm.
14 still, but the atomic number changes.
Hmm.
Yeah, continue please.
Uh, so, if we find the remains of a dead creature whose 14 to carbon 12 to carbon 14 ratio is half of what it's supposed to be, we can assume the creature has been dead for about 5,730 years. Uh, if the ratio is a quarter of what it should be, we can assume that the creature has been dead for 11,460 years, about 10 half-lives. The amount of radiocarbon left becomes too minuscule to measure, and so this technique is useful for dating specimens which died more than 60,000 years ago. Another limitation is that this technique can only be applied to organic material such as bone, flesh, or wood. It cannot be used to date rocks directly.
So it's clear, right? Done.
Hmm.
And here we are
Hmm.
seeing the diagram, right? How the
Hmm.
half-life is working with carbon 14 dating.
Hmm.
This one already you understood, right?
Hmm.
Hmm? This
Yes,
half-life.
yes, yes. Easy.
Yeah, the similar one we discussed before.
So, sir,
Done.
next class will we
This
discuss
this
the
topic is done. Next class means we are not done. We are still in the class, huh? And
hmm.
we are done with the notes only now. And I told you to try the worksheet as much as
Yes.
possible.
Hmm.
So did you try the worksheet?
Yes, I completed the MCQs only, and some of the extended.
Okay, great.
50%, 40% of the extended.
Okay, okay. I check now that how much you did.
Hmm. So, sir, should I send you the pictures?
Yeah, you should open your worksheet.
Hmm.
This one is the worksheet, right?
Yes.
So what is the answer of one?
So it's neutron and I B. Sorry, C.
Correct. Then two.
So this one is B.
Bangladesh.
Bangladesh.
Then
So this one I did not mark.
now do.
Now which statement about the reactor in the nuclear fission is correct?
Is coming from the block diagram, power station block diagram. It is thermal power station, right?
Which of the reactor in the nuclear? The main reaction. No, A, not A. D. Sorry, isn't it C?
Yes.
Hmm.
And then four.
I said this one is said this one I did not mark.
Read, then mark now. Now you are done with the topic, right?
Hmm. The result of the alpha particle scattering experiment a variance for which of the following? So this one is the nuclear atom.
Yes, correct. And then five.
Uh, so this one is C.
How?
So it's A.
A. A is correct, huh?
Hmm.
Six.
B. Bangladesh.
Both isotopes have the same number of protons in the nucleus. Yeah, it's very simple, right?
Hmm.
Then seven.
Sir, A.
Correct. Eight.
D. Dhaka.
Beta emission, right?
Yes, D. Dhaka.
1632, correct. Nine.
C.
Which one?
It contains two more neutrons.
Two more neutrons. Yes, correct. 10.
10A.
And mm, yeah, correct. Correct. Then
Uh,
11.
11 I did not mark because I did not
Now,
study the
now you do. Now you do 11.
sample contains atom of an isotope that has a half-life of 7.2 years, which quantity halves every 7.2 years. The mass of a sample, sir, it's the mass of a sample.
No,
Is it B? Yes.
no.
What? It's C.
See. So why it's not A, why it's not B? I'm explaining here. The mass of the sample remains same because the product is also there, right?
Hmm.
So
Sir, but total 60.
if they are saying if they are saying exactly the way that isotopes mass is becoming half, then we can take this. Okay, sample when it's becoming after half life, in that sample also we have the product. So the mass of the sample will remain same. Like if it was 8 gram, it's still 8 gram, but the
Hmm.
mass of the isotopes is becoming half. Okay, radioactive isotope. Is it clear?
Yes.
And another thing is nuclear number. Nuclear number will not be half. Nuclear number, what happens if it is beta decay, then one nuclear number will be same. What will happen? The atomic number is changing, right? If it's
Hmm.
emitting, if it's emitting alpha particles, then its mass number is changed by 4, not it's becoming half. Is it
Hmm.
clear? So we cannot say it. But the number of
Yeah.
atoms of the isotope, number of mass of the isotope, if it is saying this way, then we will choose that option. Is it clear? Or number
Yes.
of nuclei of the isotope. Nuclei means atoms, right?
Hmm.
Nucleus. So if it is number of atoms, number of uh, mass of the isotope, or the mass of the isotope, or number of nuclei of the isotope, that one will accept. Or the uh, count rate is becoming half of the sample. Is it clear?
Hmm. Hmm.
Emissions of the emissions of the sample is becoming half. Huh? That one we
Hmm.
can take as a half life. Is it clear how to deal?
Hmm.
So here till here we are done. I will upload the mark scheme of MCQ part, okay, tonight. Then you finish the MCQ part, try it, huh? Is
Hmm.
it clear?
Yes.
If I upload the mark scheme, it will help you, right,
Hmm.
to analyze your questions. And if you have any of the questions still doubt, that one we can only discuss. Then we'll go fast with structured part. So how you are feeling about the nuclear physics? It's now confident, right?
Yes.
Okay. Thank you so much. Thank you. Allah Hafiz.
Love us, sir.